Well, now let's get back into our apparatus that we showed you before. That we have the light which is shining our sample. We have the incident light, and now we have here the scattered light which reaches the detector, and you see that based on the movement of these particles, the scattered light, depending on being constructive or destructive, is changing when it reaches the detector here. Okay, but I told you before that the rapidity in the change of this intensity of the light is directly proportional to the movement of the particles within the medium. Okay, the smaller particles, because they have the larger diffusion coefficient, they are moving more rapidly within the medium, and as a matter of fact you will see that the light intensity is changing more rapidly. On the other hand, for the larger particles, due to the fact that the diffusion coefficient is smaller, so they are moving more slowly. I showed you within the first video that the larger particles move more slowly. So this change in the light intensity is going to be more slowly as a result. So this is exactly what we want to use to decode the information. Okay, you see here that after reaching the detector, the information about the intensity of the light are sent through this cable into this correlator. But what is this correlator? What is its role and what is it going to do? Okay, this is a machine that is going to decode the information about the size of the particles. So here we are going to introduce some purely mathematical and statistical descriptions. So I want you to be focused and keep your heads up, because it might be a little bit confusing. But don't worry, try just to concentrate and understand the physics of the problem. So up until now, we just mentioned that based on the information which are encoded within the change of the pattern in the light intensity, we are going to extract the information about the size of the particles. Okay, well, first of all, I want to go for the correlation, and then we will introduce the autocorrelation, and after that we will go for the use of autocorrelation for the patterns that we got, that our detector got, okay, to analyze them and extract the information about the size. So let's now start with the correlation. What is the correlation? Correlation is simply a measure of how similar two signals or two patterns are going to be. Okay, well, you see here that we start from the number 1, 3, minus 2, and 4. Number 1, 3, minus 2, and again 4. So we increase, decrease, and increase. And here you see that again we increase, decrease, and increase. So these two signals, they seem to have the same behavior, the same pattern. Okay, but how about this one? You see here that instead of the increase that we had here, we have the decrease, and instead we have the increase here and again the decrease. It's something exactly the opposite of what we had seen here and here. Okay, so this signal must be different from these two. But how can we quantitatively show that these three signals are similar or different compared to each other? Well, we introduce this formula for the correlation of the signal X and signal Y. And it says that we just have to multiply the xn and yn together, okay, and sum them, and we will have the correlation. Well, if we multiply the x1 with the y1, these are 1 and 2, and 3 by 3, minus 2 with minus 1, and 4 with 3, and sum them together, you will see that we will reach to the number of 25. This number is a big number, and it gives us the information that these two patterns are similar to each other. However, for the comparison between these two signals, okay, if we multiply the 2 by 2, 3 by minus 1, minus 1 by 4, and 3 by minus 2, and again we sum them, we get the number of minus 9. And because this is a small number and minus, you see that these two patterns are not behaving the same. Well, but there is some problem with this approach. If I change this number 2 with the number 100, then 2 multiplied by 100 will be 200, and when I substitute it here, you see that instead of having 2, I have the 100. You see it increases a lot until here. And when I again measure this number, I will reach to 187, which is a really big number. But does it really mean that the pattern that I see here is similar to this pattern? No, it doesn't mean that, because although this number is so big, bigger than 25, but it is not behaving, this pattern is not behaving like that. So there must be a problem, okay? We must normalize our calculations. So let's have another look at what we have done. You see here that we measured the correlation between x and y with 25, then we substituted the 2 with 100, and for y and z we got 187, which is a bigger number. But the problem is that, as we saw, these two curves are not behaving similarly. So there must be a problem, because this number is bigger than 25. So does it really show that these two curves are behaving more similarly or not? Well, as we saw, for sure they are not behaving similarly, but x and y, they were more similar. Well, we have the correlation here, and this is the formula that we used before. Now we are going for another formula, which is this one. You see here that for the normalized correlation of x and y, we have this expression here exactly in the denominator, and within the denominator we have two more terms: the sum of the x2 and the sum of the y to the power of 2, and finally the square root of them. Well, this approach is now going to give us more reasonable quantitative information for comparing these two signals and these two signals. if we calculate the normalized correlation for the function for the signal x and y, you see here that we will reach to before we calculated the nominator here, and we got the results of 25. And now if I calculate the denominator, you see here the 1, 3, minus 2, and 4, and I square them, and then I sum all of them, and again here 2, 3, minus 1, and 3. I square them and sum all of them. Then I multiply these both together. You see, both of these to multiply together, and finally I get the square root of the final result, and it's 26.27. Okay, so this is the number, the result for the denominator. So 25 for here and 26.27 for here, and the division of these two reaches to the number of 0.95. So it is really close to the number 1. Okay, and now because it is normalized, it tells us that these two functions x and y are behaving really similarly, okay, together with compared to each other. Now let's go and do the same for y and z. Well, if I do the same for y and z, within the denominator we had the 187 here, and within the denominator for these two signals I will reach to the number 490, and the division of 187 to 490 will give us the final result of 0.38, which is far from 1 compared to the 95.95, because these two functions are not behaving more similarly compared to these two signals. Okay, now we use the normalized form. So this is the concept that we are going to use for getting the information about the size of the particles out of the pattern that our detected gives us. Okay, I see that I have talked for 13 minutes. Now let's go to the next video.